On November 5th, 2018, a signal began its journey home. It left a spacecraft 11 billion miles from Earth, traveling at the speed of light, and it still took 16 and a half hours to arrive. When it finally reached the giant dish antennas of NASA's Deep Space Network, the scientists reading it did not immediately understand what they were looking at. The data showed something strange happening all at once, across 4 separate instruments, in a way that shouldn't have been possible unless one very specific thing had just occurred. A spacecraft, the size of a small car, launched during the Ford administration, running on technology older than the personal computer, had just become only the second human-made object in history to leave the boundaries of our solar system entirely. Its name was Voyager 2, and what it found, the moment it crossed that line, did not just confirm what scientists already suspected about the edge of our solar system. It broke it. This is the story of that crossing. What Voyager 2 discovered in the region, no human instrument had ever independently verified before, and why. Right now in 2026, this nearly 50-year-old spacecraft is fighting the same battle for survival its twin has been fighting, racing against a power supply that is running out 1 watt at a time. I'm your host, and this is your channel. If this is the kind of story that keeps you up at night, subscribe now, because we're just getting started. To understand why the moment Voyager 2 crossed out of our solar system mattered so much, you have to go back 6 years earlier, to a much messier, much more uncertain first attempt at the same feat. In August of 2012, Voyager 2's twin, Voyager 1, had become the first spacecraft to cross what scientists call the heliopause, the invisible boundary where the sun's constant stream of charged particles, the solar wind, finally loses its battle against the pressure of interstellar space pressing in from outside. Crossing that boundary should have been simple to confirm. The spacecraft's plasma science instrument, the one specifically designed to measure the speed and density of the solar wind, would show it dropping to nothing, and the interstellar plasma, on the other side, would show up instead, denser and colder. Except Voyager 1's plasma instrument had stopped working back in 1980, damaged during its flyby of Saturn, decades before it ever got close to interstellar space. So when Voyager 1 actually made its crossing, scientists had to reconstruct what happened using indirect evidence, a spike in cosmic rays here, a drop in heliospheric particles there, and it took an entire extra year, until 2013, before they had enough confirmation to say with confidence that the historic crossing had actually happened, back in August 2012, retroactively. It was a monumental achievement wrapped in a frustrating amount of uncertainty, because the one instrument built to give a clean, unambiguous answer had already failed. Voyager 2 did not have that problem. Its plasma science instrument was still working. And that single fact turned its crossing, 6 years later, from a confirmation into a genuine, real-time scientific event, the first time humanity would get a clean, direct, instrument-verified measurement of the moment a spacecraft actually left the solar system. Ed Stone, the mission's project scientist at Caltech since 1972, stood in front of reporters at a meeting of the American Geophysical Union in December of 2018 and explained exactly what the team had seen. 3 separate independent lines of evidence, all lining up at the exact same moment, all pointing to the same conclusion. First, the cosmic ray subsystem detected a sudden, dramatic jump in high-energy particles arriving from outside the solar system, the kind of galactic radiation the sun's magnetic bubble normally deflects. Second, the low-energy charged particle instrument recorded a sudden drop in particles native to our own solar system, the kind produced by the sun itself. Third, and most decisively, the plasma science instrument, the one that had failed on Voyager 1 decades earlier, registered exactly what theory predicted it should: a sharp collapse in the detection of solar wind all the way down to background levels in 3 separate directions simultaneously. All of it happened within the same narrow window of data, confirming that Voyager 2 had crossed the heliopause on November 5th, 2018, at a distance of just over 11 billion miles from Earth. For the second time in human history, and for the first time with completely unambiguous, real-time instrumentation, a spacecraft built by human hands had left the protective bubble that has surrounded every planet, every moon, and every living thing our species has ever known. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, said at the time that the team was happy and relieved the mission had lasted long enough to reach this milestone at all, and that the real excitement was just beginning, because for the first time, scientists would have 2 independent datasets from 2 different locations along the edge of the solar system to compare against each other. And what they found when they finally compared those 2 datasets did not confirm the tidy, symmetrical picture of the solar system's edge that most models had predicted. It broke it in ways that took researchers by surprise. The first surprise was where the crossing happened. Voyager 1. crossed the heliopause at a distance of about 121 astronomical units from the Sun, with 1 astronomical unit being the distance from Earth to the Sun, roughly 93 million miles. Voyager 2 crossed at almost the exact same distance, about 119 astronomical units, despite heading in a completely different direction through space. On its own, that might sound like a tidy confirmation that the heliosphere is a fairly uniform, symmetrical bubble, but the timing made that coincidence deeply strange. Voyager 1 made its crossing during a period of minimum solar activity when the Sun was relatively calm. Voyager 2 crossed 6 years later, during a very different phase of the solar cycle. Existing models of the heliosphere predicted that the boundary should expand and contract like a lung, breathing in and out with the rhythm of solar activity, meaning the two crossings, happening under such different solar conditions, should have occurred at noticeably different distances. Instead, they happened at almost the same distance, and researchers like Stamatis Kremigis at Johns Hopkins University openly said the coincidence was puzzling, sitting outside what current models of the heliosphere were prepared to explain. The second surprise was the temperature. Just outside the heliopause in the true interstellar medium, existing models predicted a relatively cool, calm environment somewhere in the range of 10 to 30,000 degrees Celsius, based largely on what Voyager 1 had found back in 2012. When Voyager 2 crossed 6 years later, its instruments measured a temperature closer to 30 to 50,000 degrees Celsius immediately outside the boundary, hotter and more energetic than the earlier crossing had suggested. This is not fire in the way you'd picture flame or combustion. It's a matter of charged particles moving at extreme velocities, generating temperatures that would be catastrophic to any physical material, but exist in a region so sparse, so close to a true vacuum, that the concept of temperature behaves very differently than it does in the thicker atmosphere we live in on Earth. Even so, the discrepancy between what Voyager 1 measured in 2012 and what Voyager 2 measured in 2018 told scientists that this boundary is not a fixed, unchanging wall. It shifts, it varies, and a single measurement from a single location in a single moment in time cannot tell you what the whole boundary looks like. The third finding was, in some ways, the most quietly unsettling. Right at the edge, just inside the heliopause before the true crossing, Voyager 2 detected something Voyager 1 had never reported. A distinct magnetic boundary layer with unusually powerful, compressed magnetic fields sitting right at the threshold before the spacecraft finally broke through into interstellar space. And on the other side, once truly in the interstellar medium, both spacecraft found something that ran directly against decades of prior assumptions. Scientists had long expected that the Sun's magnetic field, carried outward by the solar wind, and the separate magnetic field of the wider galaxy outside the heliosphere would be two distinct, largely unrelated systems, meeting at a clean, sharp boundary with very different orientations on either side. Instead, both Voyager 1 and Voyager 2 found that the magnetic field just outside the heliopause runs roughly parallel to the magnetic field just inside it. The Sun's magnetic influence and the galaxy's magnetic environment are not cleanly separated at that boundary. They appear to be connected, aligned, interacting in a way that no model had confidently predicted before either spacecraft actually measured it directly. And then there was the discovery that gave researchers pause about how well sealed our solar system's protective bubble actually is. One of Voyager 2's particle instruments detected something researchers described using a simple, almost domestic metaphor. If the heliosphere is like a ship sailing through interstellar space, the hull of that ship is somewhat leaky. A steady trickle of particles from inside the heliosphere, essentially matter that originated within our own solar system, was found slipping through the boundary and out into true interstellar space. Detected more than 100 million miles beyond the heliopause itself. The boundary that separates everything humanity has ever known from the vast dark ocean of interstellar space is not a perfectly sealed membrane. It leaks, and the two spacecraft, crossing at different points along that boundary, found the leakiness was not uniform either. Voyager sans marque. One, which crossed nearer to the front of the heliosphere relative to its motion through this galaxy, found a stagnation region where the solar wind's forward motion actually slowed to zero before the crossing. Voyager 2, crossing closer to the flank of the bubble, found no such stagnation region at all, but instead found this porous, leaking boundary that its sibling spacecraft simply hadn't encountered in the same way. All of these findings, the puzzling symmetry and crossing distance, the unexpected temperature spike, the newly discovered magnetic boundary layer, the parallel magnetic fields, on both sides of the heliopause and the leaky, asymmetric nature of the boundary itself, were published together in 5 separate papers in the journal Nature Astronomy in November of 2019, exactly 1 year after the crossing. Taken together, they didn't just confirm that Voyager 2 had left the solar system, they forced an entire generation of heliophysicists to rebuild their mental model of what the edge of our solar system actually looks like. not as a clean, symmetrical, predictable sphere, but as a dynamic, shifting asymmetrical boundary that behaves differently depending on where you cross it and when. Now here's where the story becomes something closer to a race against time, because none of this stopped mattering once the headlines faded in 2019. Voyager 2 is still out there right now, still transmitting, still one of only 2 human-made instruments anywhere that can measure the true interstellar medium directly. And just like its twin, it is running out of power. Voyager 2 draws its electricity from the same kind of source as Voyager 1, 3 radioisotope thermoelectric generators converting the heat of decaying plutonium into usable current, losing roughly 4 watts of output every single year, a decay that no engineering fix can reverse. In March of 2025, the mission team made the same difficult call for Voyager 2 that they would later be forced to make for Voyager 1 in 2026, shutting down its low-energy charged particles experiment, one of the very instruments that had helped confirm the historic 2018 crossing in the first place, in order to keep the rest of the spacecraft's systems alive a little longer. As of early 2026, Voyager 2 has 3 functioning science instruments remaining, slightly more than its twin, and it currently sits roughly 13 billion miles from Earth, still transmitting engineering, data, and interstellar readings on a daily basis, still traveling at around 35,000 miles an hour into a region of space that remains almost entirely unexplored by any other instrument humanity has ever built.